More than 1 million students are taking admission in computer engineering every year. But only few thousand are getting placed in their dream companies. So what you think? What is the reason behind this? Actually, this is all about consistency and step-by-step guided preparation. I'm happy to announce you that iNeuron is coming up with DSA Foundation course specially curated for product-based companies. So if you are targeting for Mang companies or any other product-based companies, please join this free course. For more detail, check out the description. The classes will start from 24th Jan, 5 p.m. Best of luck. More than 1 million students are taking admission in computer engineering every year. But only few thousand are getting placed in their dream companies. So what you think? What is the reason behind this? Actually, this is all about consistency and step-by-step guided preparation. I'm happy to announce you that iNeuron is coming up with DSA Foundation course specially curated for product-based companies. So if you are targeting for Mang companies or any other product-based companies, please join this free course. For more detail, check out the description. The classes will start from 24th Jan, 5 p.m. Best of luck. Hello everyone, welcome back to the DSA Foundation course, specially designed for product-based companies. Nice to see you back, Karthik, Jayashri. Welcome back. Okay, so before moving on, okay, let me tell you people, this course is designed for preparing for product-based company, especially product-based company. So if you are dreaming about, maybe today, you are dreaming about product-based company, or maybe you will dream, definitely you will dream about it, maybe after 5 years in service-based company. In that case also, definitely you need to switch. That will be requirement also. So in that case also, again, you need to think about the building your DSA foundation. So this course is about building the DSA foundation, especially for the product-based companies. Okay, so for the new people, let me tell you, for the new people who have joined here, who are new here, let me tell you, this is the third class. This is the third lecture. Already 2 lectures I have already completed in this series. This is the series of 18 lectures. Okay, we are going to cover all the most important topic in DSA here in this class. And the motive of this series is to build your foundation, DSA foundation for product-based companies. Okay. So in the first lecture, we just discuss about the motivation, why you have to study the DSA. And the second lecture, we discuss about the time complexity analysis. And today we will discuss about the asymptotic notations. With asymptotic notations, we will also cover the space complexity analysis, and we will also find out the time complexity of recursive codes. Okay, so this is the target for today. So let's see how much we are able to cover up. We will start from the asymptotic notations. So, okay, fine. Good evening, Pankaj. Hello, Akansha. Good evening, Amit. Karthik, I will accept the answer only in the comment. Okay, give the answer in the comment in the for the second lecture, Karthik. Okay, Jayashri also is sharing the answer of previous class. Please let's discuss this thing in the comment of previous class. There I will definitely reply 101%. Yeah, hello Kunal. Okay, fine. So okay, before moving on further again, first of all, I want to wish you everyone happy Republic Day. And Thomas is saying that, okay, I have started this series little late. I'm trying to keep up. It's okay. Only 2 lectures I have delivered till now. You can take these 2 lectures, and for this lecture, you do not need anything. Let me tell you people, if you are watching this video, you have not watched any of the previous video, you can watch it independently. Okay, I'm designing these lectures such that anybody come, he's just roaming around the internet, and by chance he get landed in one of the lecture. he can come here. He is welcome. He is welcome and come here, get the knowledge, and he can go. That's it. No prerequisite, nothing. Just your response is required. Just your replies is required. That will be the requirement. Okay. Okay, fine. So before moving on with this lecture, let's uh, celebrate a little bit Republic Day. So let's celebrate for only 1 minute. Let's celebrate our Republic Day so that we can unite. Okay, and we can proceed with more energy. Okay. Okay, fine. So let me move my laptop this side, and so let me see, where is my cursor. Okay, I think I need to connect it first. Just a minute. Just give me a minute. Okay, fine. I think we are connected. Yes. Okay. So just for Okay, so this was a salute to our martyrs and to our country. So we are, as a country, we are growing up. Okay, so now let's move to our session with lots of energy. Okay, with lots and lots of energy, let's move toward our this session. So I will try that. Okay, you become able to get each and everything about asymptotic notations, which is, we are going to cover today. So we have already covered. Okay, this is the complete series of DSA which we are going to cover. We have already covered motivation to study DSA. Let me take the pen. We have already covered motivation to study DSA. We have covered the time complexity for the loop part. Remaining, okay, little bit remaining part we will be covering here with the asymptotic notations. After that, okay, next topics will be like this. You can check out. This is the further lectures which we are going to cover. The classes will be from Monday to Friday. The classes will be from Monday to Friday. And once again, I want to repeat, if someone is new here, let me tell you who will get benefited from this course. First one, who are very beginner. They will get benefited from this course because I'm going to start from very basic. But the advanced learner can also join this course because I'm going to cover very interesting problems in every lecture. Okay, very interesting problems. Even I'm covering the basic, I will cover the interview questions in those basics. Okay, fine. So advanced learner are also welcome to this course. And third type of learner can also join this course, who are already working in some service based company and they are trying to jump to the product based company. Okay, so for them also this is going to be a very beneficial course. Okay. Okay, fine. So let's start with today's topic, that is asymptotic notations. Let's start with today's topic, that is asymptotic notation. Fine. Let me erase this. Okay. In yesterday class, okay, we discussed about different complexity functions. Okay, I'm not taking anything from the yesterday class. I'm just uh, telling you, must be already knowing this stuff. Even you don't know, you can check out right now that, okay, these are the complexity functions like constant, logarithmic, linear, quadratic, cubic, polynomial, exponential. Okay, and so these are the different complexity function, how we represent the complexity of an algorithm with the help of these complexity function. These are some of them. These are some of them which are After that, we keep combining them with each other, make the other ones like n log n, log of log n, okay, or many others we can make. But these are the basic one. Okay, so we know this thing that okay, if your algorithm is taking constant time to execute, constant time, that is the means your algorithm is the best algorithm that is consuming the lowest time. Okay, constant time means lowest one, exponential means highest one, exponential means highest one, like exponential like 2 power n, 3 power n, n power n. Okay, so that exponential means your program is actually is not going to stop. For if you are giving, let's suppose 1000 n value, your program is not going to stop. So if we have small values, small inputs, still we can use the algorithms which are taking exponential time, but the input side should be small. Okay, otherwise they will not stop. And these algorithms who are taking constant time or logarithmic time, they can work for large input also. Okay, fine. So let's move with this class with the topic of the asymptotic notations now. Okay, I'm going to start now asymptotic notations. After this lecture, confirm you will be very comfortable with the asymptotic notations. Okay, that is confirmed. So please check out this thing. I'm starting from the very basic, like the definition again. What is the definition of asymptotic notations? So let me check out. Asymptotic notations are mathematical way. These are some mathematical way. This is just a mathematical way. What? For what? For representing an algorithm complexity. That's it. We are representing the algorithm complexity mathematically. Mathematically means we have some symbols with us. We have some symbols with us, like big O symbol. Okay, that have some mathematical meaning. Okay, big omega, just like an octopus. Okay, theta, small o, small omega. So these are the different symbols. They have their own meanings. These symbols have their own meaning. Okay, just this is the only thing we need to know. If somebody is writing big O, what that means is, if somebody is writing big omega, what that means is, what if somebody is writing theta, what that means is, we just need to know their mathematical meaning. That's it. That's it. This is all about the asymptotic notations. We need to know what they are telling to us. Okay. Okay, fine. So let's check out all of these different type of asymptotic notations. So different type of asymptotic notations, like big O notation represented with big O symbol, big omega represented with this, I don't know, this octopus like symbol, theta notation, little o or small o notation, little omega or small omega notation. So these are the 5 notations. We just need to know what are their meaning. Okay, that's it. If we know the meaning, we can use them to represent the complexity. To represent the complexity. What complexity? Time complexity or space complexity? Can you write in the chat box? Asymptotic notations represent the time complexity or space complexity. Can you please write in the chat box? Please keep replying. Again, this will be the requirement. You need to reply. You need to reply. Please keep replying. What's the use of these notations? Which complexity these notations are representing? Which complexity? Space complexity or time complexity? Space complexity or time complexity? Please reply in the chat box, whatever is coming to your mind. Whatever is coming to your mind, just reply. We are not here for giving the right answers. We are not here to give the right answer. We are here for learning. If we know everything, then why we are wasting time here? We must be watching some nice movie on Netflix. Why we are wasting unnecessarily time over here if we know everything? So don't worry, just keep replying. Keep replying whatever is coming to your mind. So many people are saying both. Many people are saying asymptotic notations represent the time complexity also, space complexity also. Okay. So if I'm writing like this, I'm writing that, okay, I have an algorithm. I have a code algorithm 1. I say that the complexity of my code is this. Complexity of my code is this. What you will understand? You will ask me, sir, which complexity is this? This is space complexity or time complexity? I don't know. Until unless you will not tell me, I don't know. This is space complexity of algorithm 1 or time complexity. So asymptotic notations can be used for both, for time complexity also, space complexity also. Okay, that's why we do not mention also in the definition, and we simply write complexity. We do not mention time and space because that is used for both. That is used for both. Okay, fine. Okay, fine. You can say, sir, why are you shouting then? It's so easy. Why are you shouting? So let me add one more thing so that I can shout. Let me add one more thing. This is also very important point. Asymptotic notations are used for representing the complexity of the algorithms for large input. For large input only, not for small input, for the large input. Up to how much large? How much large? N tends to infinity. N tends to infinity. What it means is that, it means is that after a certain point, maybe n value 100, after, if we are putting n value 100, and starting from the 100 going up to infinite, my algorithm will take fixed time, one fixed time. Okay, and that will be the time complexity. Before 100, if that is taking maybe something that is not behaving properly, that is sometime that he is saying that, okay, I will take constant time, and sometime he is saying that I will take order of n time, sometime he will say that I will take order of n square time. He may be dancing like this before 100 value. Okay, but after 100 he immediately saying, okay, I will take only n square time. Then I will say that, okay, your complexity is n square, because after 100 till the infinity you are taking n square time. Okay, so your complexity will be n square. Okay, so what I want to say simple, whenever we find out the time complexity or space complexity, we find it for large value. We find for large value. Okay, my hand is also going out of the screen. That is showing that up to infinity, Okay, there is a one question. Let me take one or two questions, then we will move with the asymptotic notations. So NGP is asking for, let me share the question with you people. Sir, can you please use daily practice problem according to the respective lecture? Okay, I will provide that. I will provide the daily practice questions also. Fine. Raghuvendra is asking for, sir, DSA with Python, will you explain with implementation in VS Code or any other IDE? Actually, I will work on lead code. Okay, on their platform itself, lead code. Okay, fine. Fine. Okay, let's start with our asymptotic notations. Okay, just see it carefully, then you will not forget in your life. See it carefully. Let's understand it by intuition. Okay, big O notation. Okay, let me write over here. Let me use the big O notation. I'm writing an algorithm 1. Okay, like this. Okay, so okay, what you mean by big O notation? Big O notation actually shows the worst case time complexity. Time taken by an algorithm. What is the maximum time taken by an algorithm? Or I can say it shows the upper bound. What is the maximum time taken by an algorithm? What that means is, okay, we can understand that from this example. Let's suppose one of the student comes to me, he write an algorithm 1. And he is saying that, sir, my algorithm will take big O of n square time. What he is saying to me, sir, my algorithm will take big O of n square time. He is making this statement. What I will understand from this is, he is trying to say me that, sir, give any input. sir, give any input to my algorithm. Maybe, okay, this algorithm is for sorting the number. Okay, so he write the algorithm for sorting the number, and he is saying me, sir, give any input to my algorithm. Any input means you give the number in increasing order, maybe in decreasing order, or shuffle them. Anyway, whatever you can do with the numbers, you do, please. But my algorithm will not take, this algorithm will not take more than n square time. That will take maximum how much time? N square time. That will not take more than n square time. That will not take more than n square time. That is telling me the worst case time complexity of his algorithm. The upper bound, what can be the maximum time taken by this algorithm, is n square. That's it. This is just a symbol. This big O is just a symbol, and this is providing us this information. That's it. That's it. This is whenever somebody use this symbol, I will understand that he is saying me the worst case complexity, the maximum time taken by his algorithm will be n square. His algorithm 1 will not take more than n square time. He is trying to say me this thing. Okay, he is trying to say me this thing. Let me add one more thing over here. In the big O notation, let me add one more thing. Big O notation shows one relationship also. Okay, what is the relationship? This is the relationship. Left hand side is smaller than equal to right hand side. So whenever we will be comparing two algorithm, okay, so let me erase this, and let me write over here one relationship between two algorithm 1 and algorithm 2. Let me show this relationship with the help of the big O notation. With big O notation, we are showing the relationship between them. So what I will understand from this, okay, can you people write in the chat box? You people please try. If you will try, then that will be more beneficial. Okay, you people please try. So can you tell me in the chat box, please, which will take more time, algorithm 1 or algorithm 2? Can you please write in the chat box? Based upon this relation, big O notation is behaving like this. I'm telling you, the big O notation is behaving like this, and I'm showing the relationship between algorithm 1 and algorithm 2 with big O notation. Can you write in the chat box? Can you tell me which will take more time to execute, algorithm 1 or algorithm 2? Please reply. That is important. Please reply. That is important. Which will take more time, algorithm 1 or algorithm 2? Okay. Some people are saying algorithm 2, and some are also saying algorithm 1. Actually, I cannot comment. I cannot comment which will take more time. Why I cannot comment? Although this might be looking like that. Based upon this relation, this is might looking like that. Okay, right hand side will always be greater than left hand side. But right hand side can equal to also. They both can be equal to also. Okay, it's not compulsory that right hand side will always be greater than left hand side. It's not compulsory. I'm telling you, it's not compulsory. The equal to is written here, so they can be equal also. I ask you question, which will take more time, and you are saying right hand side will take more time. But they can be equal to also. What statement will be the best one? Which statement will be the best one? What the hell is this? Okay, what statement we can make in this? The statement can be algorithm 2 can take more time or equal time to algorithm 1. This statement I can make. Algorithm 2 will either take more time or equal time to algorithm 1. This is the best statement. Okay, this is the best statement. I will use it actually. This will be used when I will be explaining other notations also, like small o notation, then that this concept will be much will be used. Okay, so right now just I tell you two things. Big O notation is showing the worst case time complexity of an algorithm, means upper bound. What is the maximum time taken by an algorithm? And if you are comparing two algorithms with the help of big O notation, then this is the relationship between them. Then this is the relationship between algorithm 1 and algorithm 2. Okay, this is the only thing I tell you. Okay, okay. Okay, I'm coming to your question, Vikalp. Okay, let me take the question first. So Vikalp is asking, but in small o, algo 2 is correct. I will come to small o. I will definitely come to small o. Then that will be clear better. That your doubt will be clear. Okay, fine. So let's talk about the big omega notation. Second notation, very easy, very easy. Big omega notation shows the lower bound. Means what is the minimum time? Minimum best case complexity. That is showing the best case complexity of an algorithm. Best case. What is the best case complexity of an algorithm? Okay, that is showing that thing. Lower bound of an algorithm. What is the best case? Okay. So for example, okay, if somebody is saying like this, he's saying that, sir, my algorithm is taking this much time. He have written one statement, this statement, and he give to me. He is saying me that, sir, my algorithm is taking this much time. What I will understand from this statement? What I will understand? I will understand that he is trying to say me, sir, give any input. You shuffle your input, you arrange the element in any way. Okay, you give any type of input to my algorithm 2, that will minimum will take n time. Minimum time taken by my algorithm will be n. That can be more than that. I don't know about the upper bound. See, this is important. This statement is not telling me about the maximum time. I don't know how much maximum time algorithm 2 will take. I don't know. He don't tell me with this statement. He just tell me one information. What? Minimum time. His algorithm will not take less than n time. The algorithm cannot take log n time. The algorithm cannot take constant time. The algorithm will take n time. He is giving me this information. So what this symbol is saying? This symbol is simply saying what is the minimum time taken by this algorithm. That's it. Okay, this is not telling me what is the maximum time taken by algorithm 2. What is the maximum time taken? This is not telling me. Similarly, big O also. If I'm writing about big O, let's suppose this is big O notation, showing the complexity. We are showing the time complexity of big O notation. So here, this notation, this thing is not telling me what is the minimum time taken. This is not telling me what is the minimum time taken. I don't know how much minimum algorithm 1 will take to execute. But one thing I know, what is the maximum time taken by algorithm 1? Okay, simple. This is telling me about the maximum time. This is telling me about the minimum time. That's it. This is telling me about the maximum time. This is telling me about the minimum time. He don't know about the maximum time. He don't know about the minimum time. That's it. This is what I'm telling you. That's it. Okay, fine. So let me add one more point over here. Okay, let me erase this also. Let me add one more information about big omega. The information is like this. Here left hand side will always be either greater or equal to right hand side. Here left hand side will always be equal or greater to right hand side. So this is the another information big O notation is telling me. This is the another information big O notation is telling me. Okay, and okay, fine. So let's move on. Let's move to the next notation. That's it. This is the only thing you need to know. That's it. Okay. What about the theta notation? Can you tell me? Can you people write in the chat box? What theta notation shows? Big O notation showing the worst case, big omega is showing the best case. What theta notation is showing? Can you please write in the chat box? Can you please write in the chat box? Please, everybody reply. See, the moment you will reply, you will get connected with me, and the session will go better. Then the session will go. Let's make this session much better, and that can happen only when we will be connected. I cannot see your face. Okay, I cannot see your face. I cannot know. Okay, if you really know or not. Okay, that can be only, we can only be connected if you are replying. Please reply. Let's make this session much better. Everybody, right or wrong doesn't matter, and we should not worry about other people. Okay, we should not worry. Maximum people here in the chat box is replying wrong answer. This is the question I usually ask in the interview, and maximum people reply the wrong. They says that theta notation represent the average case. No. Theta notation do not represent the average case. Theta notation do not represent the average case. Okay. So what theta notation represent? Theta notation is used when worst case time complexity of an algorithm is same as best case time complexity. When the worst case and best case both are same. Let's suppose here is an algorithm 1, its time complexity, worst case time complexity, I can represent with big O notation, that is, let's suppose n square. And the same algorithm 1, same algorithm, its best case complexity I can represent with big omega, that is also n square. Both are having the same complexity in the best case and in the worst case. Then rather than writing these two statements, I can write one statement. What? I can write that, okay, I can write algorithm 1 is equal to theta of n square. That's it. So either I can use this single statement, or either I need to use these two statements to pass the same information. What information I'm passing? I'm telling after this notation what I'm getting, what information I'm getting is that algorithm 1 complexity in the worst case and best case is same, that is n square. Worst case and best case, both complexity is same. For example, in the case of, if let's suppose the time complexity, let me write over here, the time complexity of merge sort, if anybody you know. So what is the time complexity of merge sort? So if you know, in the worst case, that is n log n. Okay, we will talk about the sorting algorithms in the sorting lecture, but still, okay, I'm telling you one thing. In the merge sort time complexity is, in the worst case is n log n, and in the best case is also n log n. Okay, so rather than writing these two statements, I can make one statement for the merge sort. I can say that merge sort time complexity is this. Okay, merge sort time complexity is this. Okay, fine. Okay, to make it clear, to make it more clear about the average case, I will take one more example. Okay, so if I'm finding the time complexity of quick sort, if you people know, if you don't know, you can check out on the Google itself right now. The time complexity of of the quick sort, not the Google. The time complexity of quick sort is, in the worst case, do you know how much is that? Anybody know? What is the worst case time complexity of quick sort? I will tell. Don't worry. If you don't know, it's okay. Just chill. We do not need to worry if we don't know anything. The people who know something, they only worry. The people who do know everything, they also don't worry. The people who don't know anything, they also remain happy. Only the people who remain in the between, they suffer. Okay. So if you don't know, don't worry. Enjoy the class. Okay, Karthik is saying that is n square. Yes. Okay, I will discuss all these things, but right now I'm just telling you the worst case complexity of quick sort is n square, and the best case is best case is n log n. Okay, see, worst case is n square, best case is n log n. These are not same. These are not same. I cannot write. I cannot represent the time complexity of quicksort with theta notation. I cannot write n log n here. This is not allowed. I cannot write this also n square, because theta notation is telling me whenever worst case and best case complexity is same. Here these are not same, these are different. This is n square, this is n log n. Here these are not same, so I cannot represent the time complexity of quicksort with theta notation. Yes, I can represent the time complexity of merge sort with theta notation, because worst case and best case both are same. Both are same. Fine, I hope you get the point what I'm trying to say. Hi Nikhil. Okay, Pankaj is asking one question. Let me clear that also. That is also nice question. Pankaj is asking that in the last class we were using this symbol. This symbol. I was not mentioning it bigo notation. Okay, if you notice that I do not use the word bigo for that. You can check out the lecture once again. I was using it because I do not tell you about the notations at that time. Okay, so I was using another word for this. The word was order of. Order of. Or what's the benefit? What was the benefit of using this word for me? This word for me, because I do not tell you about the notations, so I use this word order of. Okay, and what this order of was showing me, this was telling me approximate. What this may order of means? Approximate. Approximate. Actually, we are finding the approximate time complexity. Pankaj, we are finding the approximate. We are not finding exact time complexity. We are not finding the exact time complexity of an algorithm. Exact time we are not finding. We are removing the constant factors. We are removing the lower order terms. We are finding only that part of the algorithm which is taking maximum time. Software industry is bothered about that only. Okay, software industry is bothered about the maximum, that part of the program which is taking maximum time. See, if you are developing software for, like, let's suppose for ISRO, you are writing a code for launching a rocket. Let's suppose, okay, you have launched a rocket from here. You must be precise in that case. In that case, you are not allowed to use asymptotic notations, because you are not allowed to remove the constant factors. You are not allowed to remove the lower order terms. You need to measure each and every statement, how much time that will take, how much time that will take. Otherwise, if you are launching a satellite, that will land up in another orbit. You must be very precise how many nanoseconds, in how many nanoseconds that will be where. Okay, so in real time systems, these are known as real time systems. In real time systems, we do not use asymptotic notations. We do not use asymptotic notations. Okay, but in softwares we can use asymptotic notations, because nanoseconds do not impact us. If we are removing the constants and lower order terms, they will not impact. They will impact in nanoseconds. Okay, so as a human being, this is not a big issue for us if something delay in nanosecond is happening. Okay, so what I'm telling you is that we are finding approximate time complexity. So in the last lecture, I was using order of. I was representing this symbol as a order of, means approximate time complexity. We are finding approximate time complexity, not exact. Okay, and okay, I hope that is clear to you what I'm trying to say. So let me remove this comment also now from here. Let me take one more question because this is important. Vikalp is asking. So yes, Vikalp, DSA will be your first round. If you are going to good company, product based companies, then you cannot skip the DSA. Okay, the DSA will be the first round. Okay, so you cannot skip the DSA. You can check out on the Google itself. They have the first round of DSA. Fine, okay. So let's move on now. So I just tell you about now 3 notations. Till now I tell you. Let me erase this stuff. Let me erase. so that our board become neat and clean. So let's make it neat and clean. Let me remove this also. Okay, fine. Fine, that's it. I just tell you this thing only till now. I just share this information only. Now, let's move to the little o notation. People remains confused in little o notation actually. I see that. People remain confused. Actually, little o is somehow related to big O. Okay, little o is somehow related to big O. Little omega is somehow related to big omega. Okay, okay, let me explain little o and big O, little o notation with the help of a story. Okay, that will be easy to connect. Let me tell you a story of two friends. Okay, let me tell you a story of two friends. There were two friends. One was the boy, one was a girl. Okay, they were sitting in a park in their college. Okay, and they were talking to each other, and the same time the security guard catch them. They were doing some naughty stuff. Okay, and the security guard catch them. He catch them and take them to the professor. To a professor they take. Okay, you please come to me, the professor, you need to come. So okay, they go to the professor office. Okay, when they reach to the professor office, the boy was very clever. He was very clever, and he see that okay, the professor is, he's a DSA professor. He's a DSA professor. So he find out him. Okay, whenever when the guard actually present them in front of the professor, immediately the boy speak. The boy say that, sir, we were we were not tightly upper bound, we were loosely upper bound. He make this statement. Which statement he make? He say that, sir, we were loosely upper bound, we were not tightly upper bound. And immediately the professor listened this thing. He was DSA professor. Immediately he listened this, and he said that it's okay, you can go, you please enjoy, you please enjoy. Okay, so now okay, let's see what he said. He said, what do you mean by loosely upper bound and tightly upper bound? What that create the magic? That is the magic actually between big O and small o notation. That is the difference between big O and small o notation. Okay, so let's see what that big O, what that tightly upper bound and loosely upper bound. Okay, so that is creating the difference actually. So let's see what actually that happens, so that professor goes happy. And you people can also use the same trick to your DSA professor. Okay, whenever you get caught. Okay, okay, fine. So let me tell you what is tightly upper bound, what is loosely upper bound. Okay, two terms are there. So okay, big O notation actually, let me mention over here. Big O notation, I should mention here. Here I have space. So this is our big O notation. Big O notation actually is both. That is tightly upper bound and loosely upper bound. What do you mean by tightly upper bound? So for example, okay, your algorithm here, you have an algorithm 1. Okay, and its complexity is n. Okay, so its complexity is n. So if you are writing like this, if you are saying that okay, your algorithm 1 complexity is this, I can write this thing. I can make this statement. I can make this statement. I can say that okay, the maximum time taken by my algorithm can be n square. My algorithm 1 will not take more than n square time. Yes, I'm speaking right. My algorithm 1 will not take more than n square time. N square is bigger than n. So that will not take more than n square. This will take even n time. Okay, this will take even n time. And I can make other statement also. My algorithm 1 will take order of n time. I can speak like this also, big O of n time. So this is also fine. This statement is also fine because we know that equal to is also supported and greater than symbol is also supported. So if I'm writing greater something greater than this, that is also accepted. And if I'm writing equal, that is also accepted. But you might be noticing that, okay, algorithm 1 complexity is n. Then why we are representing it with n square? We should represent it with n only. Okay, so there might be some dilemma here. There, big O notation is creating the dilemma that, okay, what should be the complexity of the algorithm? Okay, that there might be one dilemma. This dilemma is removed by the small O notation. This dilemma is removed by the small O notation. Actually, whenever there will be loosely upper bound, then we will use the loosely upper bound. Okay, then we will use the little o notation. Whenever there will be loosely upper bound, we can use the little o notation. Okay, so for this particular thing, now we create another symbol, small o symbol, which is showing this thing, which is not showing this thing. Okay, which is not showing this thing. So for this purpose, we use the small o notation. Okay, let me give one more example. Actually, for more clarity will come. I know there will be some doubt in this, so let me take one more example. Definitely from that, everything will be clear. Okay, we get one term. Okay, lower order term here. I'm writing something here. I'm writing that. Okay, let's suppose there is a student. Let me tell you another thing. Okay, another story you can say. There is a student who write an algorithm 1, and the complexity of that algorithm was n. Okay, and there is another student 2. He write an algorithm 2. Okay, and the complexity was n square. The time taken by this algorithm was n square. The time taken by this algorithm was n. Okay, this second student goes to the professor. This second student goes to the professor. He says that, sir, this person, okay, let me give him a name, Rahul. So Rahul and maybe Amit. Amit was very clever. He goes to the professor and he give the feedback. He give this feedback to the professor. When the professor asked them, so what is the time complexity of the algorithm of both of you? Then he give this statement. He said that, sir, this is the time complexity of our algorithm. You can judge now who's taking less time, who's taking more time. So what I will understand, what I will understand from this statement? This statement I will understand that, okay, algorithm 2 can take more time than algorithm 1, or that may take equal time also. This thing I will understand from this statement, because I know that big O notation is saying that right hand side either will be greater or equal to. So actually what he's trying to do, that he's trying to put the professor in dilemma. In what dilemma? He's saying that, sir, although he's not saying wrong anything, because algorithm 2 is taking more time than algorithm 1, but he's creating the dilemma with the help of this equal to. He's trying to create the dilemma. If now in the mind of the professor will think that, okay, they might be equal also. Might be the complexity of both can be equal also. Okay, so this dilemma will be there in the mind of the professor. Big O is creating this dilemma. because Big O spot these two things. Right hand side can be greater or equal to also. So although this relationship should be represented like this is much better to represent. Algorithm 1 should be equal to small o of algo 2. This is the much better relationship between algorithm 1 and algorithm 2. Small o notation is better, is the best way to show the relationship between algorithm 1 and algorithm 2. Why? This is clearly showing the loosely upper bound. There is a direct difference between both of them. This is showing that, okay, here right hand side, in the case of small o, right hand side will be strictly greater than left hand side. See the relationship, you can see is easily. Here right hand side can be greater than equal to left hand side. Here also right hand side can be greater than equal to left hand side. Here equal to also can be there. Okay, equal to also can be there. But if there is a case, when there is a complete, there is a distinction you can make functionally. Both are different. This is taking less time, this is taking more time functionally. This is n square is greater than n. So why we represent with big O notation? So this is creating the dilemma that both can be equal. Both can be equal. It's better to use small O notation in this case when there is loosely upper bound. This is not loosely upper bound. Loosely upper bound means right hand side is strictly greater than left hand side. This is loosely upper bound. When right hand side is strictly greater than the left hand side, then we use the smaller notation. That's it. You need to know one thing only. Okay, if you don't understand anything till now, it's okay. You need to know one thing. This thing. See the difference between this statement and this statement. Here equal to is also there. Here equal to is not there. That's it. If there is two algorithm in which right hand side will definitely will take more time, functionally will be greater than the left hand side, then we will use the small o notation. Okay, then we will use the small o notation. Fine, don't worry, I will take many examples. I will give you many questions to practice. Okay, and everything will be definitely clear from that. Right now what you can do is not this point. Here right hand side is strictly greater than the left hand side. Okay, fine. Otherwise, any doubt you can ask me. Okay, so let me write important points here. Okay, so let me erase this thing also so that everything become very crystal clear. Fine, I just give you this information till now. And small omega is related to big omega. Like here, left hand side can be greater than equal to right hand side, but here left hand side will be strictly, I'm using a word strictly greater than the right hand side. Okay, so this is the relationship. So equal to is not here. Equal to is not here. Equal to can create the dilemma. Like when I asked you this question initially, most of you were saying that okay, right hand side is greater, but equal to is also there. So this dilemma is removed by both of these babies. Both these babies are helping us now. Little o and little omega. Both are little, but both are very clever. Okay. So that's it. This is the only thing you need to know. This is the only thing you need to know. Okay, I'm not going in mathematical details right now, how this is happening. Okay, you don't need to know also. But let me tell you one more thing. Okay, uh, I will be covering all this proofing also and other stuff also. After this series, I will come up with another series which will be very detailed one, which will be very detailed one, and you will get all the proof of everything. Okay, here we are using it as a tool. Here we are using it as a tool because this is a DSA foundation course. Okay, let's use it as a tool and solve the problems. Okay, let's use it as a tool and solve the problem. Note down this stuff and we can solve the problem. That's it. Any doubt till now you can ask me. Vikalp is asking very important question. Once again, Vikalp is asking so many good questions. Is this course is enough for interview round? Yes, this course will be enough for interview round, but you need to add one more thing. You need to practice after that. You need to practice. You cannot say that, okay, I take the course and I go to the interview. No, that will not work. You will be knowing the path. After this, you will be knowing everything, but you need to practice. We cannot leave the practice. DSA is just like maths only. DSA is just like math. I'm just telling you how to solve a problem. I will solve one problem only. Okay, but next 10 problems you need to solve yourself. If you will not solve, then I cannot say you can solve that in interview until unless you will not practice. DSA is just like math only. Okay, DSA is just like math. One question from Bharat Bhushan: is ISRO instead of ISRO? So actually there are okay, he is asking the question. Like, okay, Bharat Bhushan, actually, there is a two type of analysis. I'm not going in very detail, like a, a priori analysis, a posteriori analysis. Okay, so they will use the a posteriori analysis. Okay, fine. So in that case, that is, we will consider every constant also and all the lower factor terms also. That's it. Okay, fine. Take this thing only. Fine. Thomas is asking, you ask the question, then I will move on. Sir, what does left hand side and right hand side represent? Left hand side and right hand side are the, if you are comparing two functions, if you are comparing two algorithm functions, like I can write n is equal to big O of n square. Okay, so this is one function, one complexity of one algorithm. This is the complexity of another algorithm. So this is left hand side, this is right hand side. Okay, so these are nothing, these are just symbols. We do not need to get afraid from these silly people. This is just a big O notation. This is showing me worst case, that's it. And this relationship, that's it. This big O notation is showing best case or lower bound and showing this relation, that's it. Theta, when both are equal, okay, this is actually tightly upper bound. They are tightly related to each other. Worst case and best case both are tightly related, tightly related to each other. Okay, so if we talk about loosely, then we come to the small o and small omega. So this is loosely upper bound, means right hand side will be strictly greater than left hand side. Here left hand side will be strictly greater than right hand side. Okay, that's it. This is the only thing you need to know. Again, the same question. Sir, will this course will be okay for the interview stage? Yes, this will be okay, but you need to practice. You need to practice. After that, you can practice. Okay, and otherwise, don't worry. Again, I will come with, after completion of this course, I will come with a very detailed course in which we will practice also. We will practice also all the question. At that time, I will be able to say that, okay, just complete this course and go to the interview, because I will be giving you the problems. We will be solving the problems. Most important one, different logics. Everything will be used in that, different data structure, different techniques. So everything will be cleared. So in that, after that course, I can say, right now this is the DSA foundation course. So you need to practice yourself. You need to practice yourself. Okay, fine. So let's build our strong foundation first. Let's build our strong foundation. Let me erase everything here. We need to erase because we need to move on. Okay, it's exam time. So I will give you some questions and you people need to reply to that. That is important. Replying is important. I will give you questions over here. Any doubt is coming, you can ask that doubt also. Okay, but you need to reply. You need to reply to the questions. Yeah, Bharat Bhushan, you can register for the course and you will find out the practice questions over there. Okay, fine. Let's move on. So let's see. Can you answer this question first? If you can answer this question, you understand the asymptotic notations little well. So let me remove this thing. Okay, fine. Please try and please reply. Please try and please reply. That is our mantra for all the series. You need to try. It's like a math only. Until unless you will not try, what will happen if you will not try? You will lose the interest because it's a math only. You need to revise. You need to practice. Until unless that will not work. Please try and reply. That is our mantra. What should, right or wrong doesn't matter. You do not need to worry about that because actually there is a solid reason behind this. We are logical people. We must have some logic. That's it. The logic is that you are giving wrong answer. Why I'm saying that is right? Because the moment you will give the wrong answer, either wrong or right, I'm not worried about that. The moment you will give the wrong or right answer, learning will happen. Confirm. when I will explain the same concept, you will be able to understand. Even you are giving wrong answer, you will be able to understand perfectly what I'm trying to say. But if you are not trying, then there may be a doubt. Then there may be a doubt. Please keep trying. Keep trying, keep replying. Okay, let me tell you one thing. This statement is, I think, is not visible. So let me write over here. This is a hint actually for this question. The hint is like this. So this thing actually, this thing, let me write over here. So if you will sum up to n, 0 to n, and every time you are making cube of the I, you are summing up this value, then you will get this thing. So this is the formula for that. Okay. So this is the hint actually, which is written over here. Just I copy paste here. Can you tell me which is the right option here? Please try. Please everybody. Which option? I'm talking about the option. Which option is right? People are replying first option. Any other answer? Any other answer? First option is right. I'm agree with you. I'm agree with you, people. First option is right, but other option is also right. There is some other option which is also right. Can you tell me which other option can be the right one? Think over it. I can tell you the answer. See, I can directly tell you people the answer of all the questions also, but that will contribute only 20% in your learning. If I will be keep asking the question and telling you the answer, then 20% learning will be there. But if you will try yourself, wrong or right doesn't matter. The moment you will try, 100%, 100% learning will be there. If I will try, 20% learning will be there. Okay, so please tell me. First option is right, fine. What about other option? Is there any possibility other option can be right? Think over it. Please think over it. Okay, many people are replying 4 also. Some people are replying 3 also, 3 and 4. Actually, both are right. Both are right. The answer will 3 also. The answer will 4 also. There will be 3 answers for this question. There will be 3 options are right here. 3 options are right over here. Option 1, option 3, option 4. All 3 are right. So option 1 looks right because, okay, this is actually n into n square plus 1 divided by 4. So if we will solve this, this will be something like n square. This will be multiplied with this n square. And all other terms will be lower order terms. I don't know what that will be, but that will be lower order terms. Okay, and 4 is also constant. So I can remove the constant factor. I can remove these lower order terms. So the complexity should be this one. So the complexity should be n power 4. Okay, n power 4. So the option first is looking better. Okay, but for this algorithm, can I write this also? Can I write, let's suppose for this algorithm is algorithm 1. Okay, which is taking n power 4 time to execute. Okay, so can I write this also? This is can I write like big O of n power 5? Can I write like this? Can I write like this? So big O shows that right hand side will be either greater or equal to left hand side. Because is telling that, okay, my algorithm is not taking will be taking less than n power 5 time. That will not take more than n power 5 time. Yes, that is saying right. So this is greater. Yes, n power 5 is greater than n power 4. So this is greater. Due to this thing, I can say this is also right. Even I can write n power 6. This is also right. Even I can write n power 100. That is also right. Even I can write n power 1 million or 1 billion. I don't know. That is also right, because this is just saying that this thing is greater than this thing. Yes, that is greater. That is greater. So big, with bigger notation also I can represent. Okay, fine. What about small omega? Small omega is saying that, okay, this algorithm will be taking more time or equal time, to the n cube. This is what big omega is telling. More time. Sorry. So let me write over here. Algorithm 1, which is actually n power 4, that will be taking more time or equal time to n cube. Yes, this statement is also right. Yes, n power 4 is greater than n power 3. This statement is telling algorithm 1, this thing is either greater or equal to n power 3. Yes, that is greater. So this condition is also satisfied. So option 1, option 3 and option 4 all are right. Okay, all are right. Or one thing last I can add over here is that this is more right. These are not that much right, but according to their relationship, I can make this statement. Because according to what is the meaning of these symbols, according to that, yes, this statement is right. Yes, these are right. I can represent it like this also. Okay. Okay, fine. Don't worry. We will be taking lots of examples. So let me take another one. You people please keep replying. Okay. Let's practice all these notations. Let's practice. You people please reply. So please reply true and false for all these 5 statements. Whatever is coming to your mind. Please reply which statement is true, which statement is false. TF, you can write like this. TF, like that. You can write in the chat box. Please write whatever is coming to your mind. Let me tell you once again, if you want me to write, let me tell you, big O notation is telling me that worst case complexity or upper bound. Okay, and that is showing this relationship. Left hand side will be less than equal to right hand side. So this is the relationship. This is what big O notation showing. Big omega, best case, lower bound. Left hand side will be either greater or equal to right hand side. Okay. What about other notations? Theta notation we will be using when left hand side will be strictly equal to right hand side. Small o notation, baby notation. But this baby is saying that he is very aggressive. He is saying that right hand side will be strictly greater than left hand side. And there is a octopus baby also. He is also very aggressive. He is saying that left hand side will be strictly greater than right hand side. So this is the only thing you need to know about these notations, and you can answer each and every question. Please reply. Please reply in the chat box whatever is coming to your mind. TF, 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 T for true, F for false. 5 questions. Try it. Let's see it. Let's give a try. Right or wrong doesn't matter at all. That should not matter in class. That will matter, but in exam, in interview, that will matter. That should not matter in class. Keep replying, please. Whatever is coming to your mind. That's great. Many people are trying it. That's great thing. That is the required thing actually for DSA. If you are trying or not. So let me see. Uh, what about first statement? Let me try at my end. Okay. So left hand side is n, right hand side is n square. N square is greater than n. N square is greater than n. Functionally, we need to check functionally. Okay. So here we have 2n. N square is n into n, and here is n. So n into n. Even you cancel 1 n. So you can see this is n. Still n is left here. So n square is greater than n. Okay. So can I represent this relationship with big O? Let me check. Big O says that right hand side either will be greater or equal to left hand side. Yes, we can represent big O because big O is giving me this flexibility. So yes, right hand side is greater. Either anything equal to can also be accepted or greater than also be accepted. Yes, right hand side is greater than left hand side. So this is true. What about this one? Still big O notation. Both are equal. N. Both are equal. Can I show the relationship between these two functions with big O notation? Yes. Because equal to is also accepted. Equal to is also accepted. So this is also true. What about this one? Here left hand side is greater than right hand side. But big O shows this relationship. Big O says that either right hand side will be greater or equal to left hand side. Left hand side cannot be greater than the right hand side. Left hand side cannot be greater than right hand side. This is not showing this thing. So this is false. What about this one? So you can remove the constant and you can check out then. So n square is greater than n. Yes. Right hand side should be either greater or equal. This is the only thing we need to know. That is true. What about this one? Big omega. In big omega, left hand side will be either greater or equal to right hand side. Yes, n square is greater than n. Left hand side is greater than n. Yes, this is true. This is true, this is true, this is false, this is true, this is true. Any doubt in this you can ask. Any doubt in this you can ask. Spelling for each symbol. Sarang is asking, can you please write the spelling for each symbol? This is big O. In the previous slide I show you. Let me show you. So this is big O, big omega, theta, little o, little omega. So let me erase it and show you. I don't want to erase it because we have written this stuff we will be needing. So that's it. So here you can check out the spelling big O, big omega, theta, little o, little omega. Okay, fine. Fine, okay. So now let's move on. So this is actually true and this is also true. Now, okay, check out this one. Next 5. Please try, please reply. Keep trying, keep replying. Let's follow our mantra. Keep trying, keep replying. Please, everybody, don't sit idle. See, if you will sit idle, then your baby will also sit idle. Your kids will also sit idle. And their kids will also sit idle. Actually, they can ask you, Papa, you do not study. Why you are asking us to study? They can ask you this question. So let's don't ruin your complete generation. Please try. Please try. Everybody, keep trying, keep replying. Right or wrong doesn't matter, because the moment you will reply, learning will happen. Okay, let me try this at my end. Okay, big omega, left hand side will be either greater or equal to right hand side. Equal to is also there. Equal to is also there. So due to equal to, this is accepted. Left, big omega again. Left hand side should be greater or equal. Left hand side is not greater than right hand side. N is not greater than n square. They are not equal either. So this is false. Remove the constant, then we will talk. Is this greater than, is this, okay, this should be the relationship. Yeah, they are equal. Yes, they are equal. N square is equal than to equal. See, we are comparing functionally. We are comparing functionally. You remove constant factors and you remove lower order terms. So this is what asymptotic notation is allowing us. Okay, because why they are allowing us? Because constant factor impact only uh, very small difference. Okay, let me tell you the story of constant factor also. Otherwise, you will not believe me. Many people don't believe me until unless I don't tell them the story. So here is the story of constant factor. Uh, there was actually two friends, and one of them was using the Apple laptop. Okay, and he was coding in that, and another was using he was having only Pentium processor. You may, I don't know how many people know about the Pentium processor. So that is very old one processor he was having in his laptop. So he was using that one only, and both were appearing for an interview. Okay, and first friend actually write an algorithm. This one, the time taken by his algorithm was like this. Okay, and the second person who was using the Apple computer, the time taken by his algorithm was this one. Maybe I can write. Okay, uh, okay, let me write n square only. So what I want to say is that this constant factor difference, this constant factor difference is created due to hardware changes. Hardware changes, because this person might be using some old processor, so his computer is running little slow. Okay, and because that is running little slow, so that is taking little extra time. Okay, but because this person is using the latest technology, so his program is not taking this time. Okay, this extra time. So so the person, the software industry is not making the distinction between these two people just because of hardware changes. Just hardware changes is not going to impact too much. Hardware changes will not going to impact too much. It's about the logic that will impact. Maybe if this person is taking 2 power n time, let's suppose, then this person is no match for this person. This person is no match. Why? Because for n value 1000, this will wait us for lifetime. And if we are executing n value 1000 over here, this will execute in some seconds only. Okay, so This will take second to execute, this will take life to execute. So logic cannot be replaced by the hardware. So software industry is more concerned about the logic. So they are removing the lower factors because that is not going to make a big impact on the performance. Okay. So that's why we are removing the constant factor. Why we remove the lower order terms? Okay, there is a another reason, because we always find the complexity for large value. How much large? I already tell you that n tends to infinity. For lower order term, let's suppose here in this case n is the lower order term. Why we are removing lower order term? Because when n will lead to the infinity, you will see that difference between this and this will be very large. Let's suppose I put n value 1 lakh, then you can see here this will be 1 lakh square and this will be 1 lakh only. So you can see that, okay, you can say that if, let's suppose if from someone you need to take the money, you need to take the money, you need to take this much money to someone, okay, and you can say that, okay, you please leave this amount, you can leave this amount, you please pay me this one, you please pay me this one only, okay, because this is not going to impact you that much. So we can remove the lower order terms because we are finding the complexity for large value. How much large? N tends to infinity. Okay, so lower order terms will not make the impact as the n value will increase. Okay, maybe number of users who are accessing a website, web page, if increasing, then this factor is not going to impact. This is will be the reason your uh, website can go down. Okay, so this will create the reason, not this one. So that's why they are not bothered about this lower order term. Fine. Okay, so let's see over here. These are equal, so big omega is equal is allowed, so this is true. Theta notation, they should be equal, they should be equal, left and right hand side both are equal, so this is true. Right, left hand side is greater than right hand side in the case of theta? No, they should be equal in the case of theta notation, should be equal, exactly equal. Okay, fine. Fine. Okay, let me give you more question to try. Please keep trying. Try this one, please. Try this one. Let me come this side. Keep trying. Try this one. Keep trying. Keep replying. Keep trying. Keep replying. I know I cannot watch you, but God is watching. If you will not try, keep trying. Keep replying. If we are finding this information helpful for you people, if you are learning from here, please give a thumbs up. And after the session, uh, please give your comments. That will increase the range of this lecture and that will be reached to maximum students. So that will motivate me also, if I will find out that, okay, so many students are getting benefited. So that will again motivate me to come up with more series, more lectures for you people. Don't hesitate to write in the comment section and give a thumbs up, please. Keep trying, keep replying. Shivam, you are not the only one who is watching. God is also watching you. God is also watching you. If you will not try, He is watching. Okay, and let me try it at my end. So this is and this both are equal. Theta notation is used for equal only. This statement is true. This, remove the constant, then we will talk. This is n square, this is n. Functionally, right hand side is greater. They must be equal. In the case of theta, they must be equal. This is false. Small o notation, this is small o. Okay. So small o says that right hand side should be strictly greater than left hand side. Yes, this is greater than this. Functionally greater. Functionally. Okay. So this is true. Small o is not used when two functions are equal. Okay. So this is false. N cube is greater than n square. Yes, strictly greater than n square. So this is true. Fine. Last 20 question, last 5 question. Please try this. Please try this. Keep trying, keep replying. You can ask the question also if you're finding question. After this, I'm coming. Karthik is asking, what about the recursive time complexity calculation for recursive code? Okay, after this we will cover that only. Don't worry. I will finish today. I will not leave. If I'm taking more time, it's okay. I will take, but I will finish. Okay, fine. Uh, okay. Pallavi is asking why 12th answer is false. Because here is theta. And theta is used when both are equal. Left hand side is equal to right hand side. They must be equal. They are not equal. They are not equal. N square is greater than n. They are not equal. So they must be equal in the case of theta. So they are not equal. So this statement is false. I cannot relate this and this with theta notation. Theta notation show the relationship of equal between left hand side and right hand side. These are the symbols. They have some information, and we know this is the information they have. That's it. I believe that is clear now, Pallavi. Okay. Any doubt? Keep asking that doubt also, please. Okay, fine. Let me try it at my end. Remove the constant. N square both are equal. Small o cannot be used for equal. That is used when right hand side strictly greater than left hand side. False. What about this one? This is strictly greater than this. Left hand side is strictly greater than right hand side. Yes, this is that's why we use a small omega. True. They cannot be equal. Equal to is not here in small omega. False. Left hand side is strictly greater than right hand side. Yes, functionally there should be greater. True. N cube is greater than n square. Remove the constant and then see. Functionally they are not. They are equal. They are equal. Equal is not represented by small omega. This is false. That's it. I hope you get the idea of asymptotic notations. Any doubt you can ask me. How many people able to understand the asymptotic notation? Please write +1 in the chat box. Please write fast way. Please write +1 in the chat box if you are able to know what are these asymptotic notations are. You are getting, okay, what they means is, if you are able to understand that thing, please write +1. Please write +1. Don't hesitate. Please write +1. And any doubt, ask that also. Any doubt, don't hesitate for that also. And if you are really finding, again I'm saying, if you really want to give something to me also, then my fee will be like, you can go to my previous lectures. Right now you cannot write in the comment section, but right now you can go to the previous lectures, and if you find them helpful, then please you can write +1 over there, or you can write your comments over there. That will increase the range of these lectures, and I just want that maximum students should get the benefit. Okay, that's it. Okay, fine. Anand is asking why we use this. Why we use asymptotic notations means what is the meaning of asymptotic? What is the meaning? Okay, this is nice question. Let me take one question. Karthik is asking what is the meaning of asymptotic. Asymptotic means you can asymptotic is just telling you to is telling you find the approximate. You can replace the asymptotic word. Asymptotic word you can replace with approximate. That's it. Approximate. You are finding approximate time complexity. We are not finding exact time complexity because we are not. We are only checking for the loops. We are checking only for the loops or maybe recursion. We are not considering all the codes. Okay, we are just checking where we are consuming the maximum time, where our web page can go down if the size of input will increase actually. Okay, so this is what software industry is looking. Okay, so you can replace asymptotic with approximate. We are removing lower order terms and constant factors. We are getting just big factor which is impacting approximate time complexity. Thomas is asking, sir, do we use asymptotic notations for measuring a single algorithm complexity? Yes, we will use in complete series. Now I will not discuss with you the asymptotic notations. I will use these symbols because in every program they will ask you, okay, you need to solve it in big of n time, theta of n time. These symbols will come. Then you will be able to understand, okay, what I'm talking about. Okay. Okay, one question. Suraj is asking why 13th answer is true. Because 13th answer is true because this is small o. This is small o. And small o says that right hand side should be greater than left hand side. Right hand side should be strictly greater than left hand side. Yes, n square is greater than n. N square is greater than n. Yes, this is true. This relationship is happening. And that's why this is true. I have already tell you, okay, which notation to use when. Like big O notation you can use to represent the worst case complexity of an algorithm, big omega for best case complexity of an algorithm. If you are relating two algorithms, then if you're finding best case and worst case same, then you can use the theta notation. You can use small o if you're finding right side function is greater, right side algorithm is taking more time than the left side algorithm. And here in small omega, when left side algorithm, you are comparing two algorithm, and when left side function is left side algorithm is taking more time than right hand side, you are confirm about that, then you can use small omega. Fine, okay, let's move on now. Let's move on now. Any doubt you can keep asking. I will take your doubt from anywhere. But now let's move to this part. Karthik was asking this, sir, can you please cover the time complexity of recursive codes? Actually, he know that recursion is one of the most important concept. He know that recursion is one of the most important concept, and people find difficult to find out the complexity of recursive codes. Okay, don't worry. This next few slides will definitely help you. You will be able to find out the complexity of recursive codes. Okay, just you need to check out it carefully. I will come to your questions after this. Okay. Okay. Let's cover something and then I will come to your questions again. I will take your questions. Let's move on. Mm. Fine. So fine. Okay. Great. Let me now. Fine. Okay. Can you people tell me what is the time complexity of this code? Anybody know what is the time complexity of this code? This is a factorial program, and in this factorial program, to find the factorial, what do you mean by factorial? Okay, so if what is the factorial of 5? Factorial of 5 is 5 into 4 into 3 into 2 into 1. So this is the factorial. Okay, and this program will find out the factorial of a number. Any number you are providing, this will find the factorial. Okay, and Here we are using recursion actually. To solve this problem, we are using recursion. And what is recursion? Recursion is a program in which a function call to itself. If a function is calling to itself from its body, so you can see factorial name of the function is factorial here and here same. Okay, only this parameter is changing. Only this parameter is changing. Okay, so this is a recursive program. We are using recursion. We will talk about recursion in detail when we will take the recursion lecture on recursion. Okay, right now just you need to know that okay, we are solving this problem using recursion. Okay, and what is the time complexity? How many people know what is the time complexity of this code? Keep replying whatever is coming to your mind. Just enjoy it. Just enjoy it and reply. What is the what is the time taken to execute this code? But if you know this thing, you can reply, or you can give a guess also. Okay, don't need to worry about anything. To involve yourself, you just give your own idea. That's it. And this way I will be better connect with you people also. Okay, the moment you will reply, I will be get connected with you. Okay, because I will be able to find out uh, how much I need to talk, in how much depth I need to talk. Okay, fine. Okay, uh, so actually this will take order of n time to execute. Okay, because this function, let me tell you how this is executing, although I will go in more detail in recursion uh, in the recursion lecture, but still, okay, let me tell you nothing. Just we are finding the factorial of 5. So n value is 5, n value is not 0, n value is not 1. We are not going to return from here. We are coming here. What we are doing in this function, what we are doing, we are executing this statement. What we are doing, 5, n value is 5, and then recursively we calling this function again. So let me call 5 into I'm not writing factorial completely. I'm writing f only over here. Okay, what value I'm passing? 4, n minus 1, 5 minus 1, 4. Again the same function will be called. Again, this is not, n value is not 0, n value is not 1, that is 4 only. Okay, so we will come here. Fine. So this will be 4 into, again, factorial of 3. This value is not 0 and 1. So again, this will be 3 into factorial of 2. This value is not 0 and 1. Again, this function will be called, this value will be 2 into whatever is the, okay, factorial of 1. Now factorial of 1, for n value is 1, we will return 1. From here, this will return 1. So here we get 1. So this will be 2 into 1, 2. Here this will pass on 2. 2 into 1, 2. Now this will be 3 into 2, 6. So this will return 6. So 6 into 4, 24. And 24 into 5, I think 120. Okay, that is 120. So yes, we get the factorial of 5, that is 120. So we solve this problem, we find the factorial of 5 by recursion. So how many steps I have taken? How many steps? Okay, 1, 2, 3, 4, 5. 5 steps I have taken. What was the n value? 5 only. So I can say that I have taken 5 steps. So what the time complexity will be n here. That will depend upon the value of n. Whatever will be the value of n, that many functions calls I will make. Okay, so this will take order of n time to execute. Although, let me tell you, you do not need to even know the logic. You do not need to know the logic of this code also. Okay, you can directly also find out the time complexity of this code. How? That is the standard way to find out the time complexity. Actually, whenever we have recursive programs, we use recurrence relation. There is a term, recurrence relation. We generate the recurrence relation for that, and then we can solve the recurrence relation. For example, let me erase this stuff. Very easy. Just you concentrate over here. Very easy. See, this is a function. Okay, in the recurrence relation, we say that okay, this is a function. Let me write it like this: t of n. I can write factorial of n also. because we want, because the format will be same for every algorithm. This is the name of the function. Here name of the function is factorial. Okay, just we to standardize we write t over here. Okay, and n is the size of the input here. Okay, that's it. So we replace this thing with n. I'm telling you what I'm telling you how to write the recurrence relation. Let me write recurrence relation. So if you can find the recurrence relation, you can find the time complexity. Now I'm telling you how to find the recurrence relation. Very easy. How? Simply replace this with Tn. Okay. And this is the same function I'm calling. But only parameter is changed. Now the value is t minus 1. So this, the name given to this will be, the function is same. So name is t. Okay. But the parameter is n minus 1 now. The parameter I'm passing is n minus 1. Here I'm passing n. Okay. So I replace this. One more thing, one last thing. Can you tell me, you people tell me, how much time the body part of this code is taking to execute? How much time this code is taking to execute this one? Please write in the chat box. How much time these two statements are taking to execute? Can you please write in the chat box? Yeah, that will take constant time. There are some questions in the chat box, other questions also. Like Sarang, I think, asked the question. That is a very beautiful question. I will come to that. Okay. Before that, let's finalize this thing. What is recurrence relation? These three things you need to know. That's it. Let's make the recurrence relation. First, write this term. Then write this recursive term. This is known as recursive term, which is going to recurse. Okay. Equal to recursive term. Whatever recursive term we have. Second thing, we need to write this thing. That's it. Last thing, this body part, how much this is taking time. How much time this is taking? 1. This is taking 1 time to execute. How much time? Constant time, 1 time to execute. That's it. This is the recurrence relation. After finding the recurrence relation, now you can go to the Google. You please open the Google in the side. And check out. Type this thing. Type this thing in the Google and ask, what is the time complexity of this recurrence relation? Please type in the Google and please reply over here. What is the time complexity of this recurrence relation? Please type in the Google and ask to the Google. Let's use the Google in for learning, actually, not for cheating. So if you just simply write Tn equal to Tn minus 1 plus 1, and you can write what is the time complexity. Or if even simply you will write this thing also, they will tell you the time complexity for this is actually order of n. That is order of n. The time complexity will be order of n. So 2 steps are there to find the time complexity of a recursive code. First step, make the recurrence relation. You know how to make the recurrence relation. Simply replace this with this recursive term like this. And check out the body part is taking how much time to execute. So 3 things are there. This is the function name. Let me write function name. And what is this? Recursive term. Recursive term, which is making the recursion. Okay. And what is this? This is telling the time taken. Time taken to execute the function 1 time. If we are executing this function 1 time, how much time this will take? Constant time, because there is no loop inside it. There is nothing in this code. So this will take constant time. So that's why we write 1. If this is taking n time, then we write n here, or whatever is coming, n square. So this is the recurrence relation. First step, create the recurrence relation. Very easy. We create the recurrence relation. Second step, Now solve this recurrence relation. Second step is solving the recurrence relation. Actually, we can solve the recurrence relation by using different methods. There are different methods to solve the recurrence relation. One of the famous one is the master method. Okay, like recursive tree method, recursive tree method, iterative method, iterative method. So let me write here, like next one can be substitution, substitution, and there are other methods also. Okay, these are the popular one. Right now what you can do is you can just write this recurrence relation in the chat in the Google, and you can find out this thing. Okay, you can find out this thing. This require further at least covering all that stuff require further at least 3 to 4 hours. Okay, so I'm not covering this in this session. Okay, I will be covering this, but don't need to worry. I will be covering this stuff in the series, in which after this series I will be taking another series in which I will be going very depth, and I will practice over there itself with you people, and in that place I will covering this. Okay, right now you can note one thing, that okay, recurrence relation we have generated, and you can find this. Okay, how much you can just write in the Google, and you can find okay how much time this is taking. Okay, how much time this is taking. This is taking order of n time. Order of n time. Let me give you more intuitions. You can find with the help of intuitions also. Okay, let me give you the intuitions. You will find this thing easy. Let me give you the intuitions. And before going to that, so let me show you the time complexity is n here for this code. So, and the recurrence relation is that Tn equal to Tn minus 1 plus 1. Fine. Let's move to the another code. Can you people tell me what is the time complexity of this code? If any one of you know, can you tell me what is the time complexity of this code? Meanwhile, let me take some of the question from the chat box. You people, if anybody know, please reply in the chat box. What is the time complexity of this one? You will become very comfortable. Don't need to worry about solving of the recurrence relation. Okay, don't need to worry about how to solve the recurrence relation. Don't need to worry about that. Just try this one. This is more important, believe me. Can we write okay, Sarang was asking for the factorial program. He was asking a question that okay, can we write theta of n in place of big O of n? Yes, Sarang, you are right. We can write theta of n for factorial. Okay, because minimum time taken, the time complexity to find factorial of a number, you cannot skip like 5 into 4 into 3 into 1. You cannot directly find the complexity of 5 factorial. You cannot find directly somehow in constant time or in log n time. Minimum time you will be requiring how much? N. Maximum time again n. So it's better. You are right. Why you are writing with big O? It's better you write with theta. Yes, you are right actually. This is much better. Because with this, we are providing two information. What? The minimum time taken to find the factorial is n, and maximum is also n. So let's write it with theta. When minimum and maximum both are same, it will be better. You are right actually. Okay. So let me see what the people are replying to this question. Oh, Vikalp also come up with the recurrence relation. You need to improve this recurrence relation, Vikalp. Little bit improvement is needed over there. Okay, fine. Otherwise, that's great. You people are trying. Yes, time complexity is log n. You people are right. The time complexity is log n over here. Maybe you know directly. Don't need to worry. How these people know? Actually, they have already studied it earlier. Okay. It's not a magic. Nothing magic will be going on. They know this thing. They have studied earlier. They know when we will also study, we will also be knowing. That's it. So this is actually binary search, one of the famous algorithm, one of the famous searching algorithm. Okay, and binary search take log n time. Every time we talk about the log n complexity, the binary search should come into the mind actually. Okay, so they know this thing actually. That's it. Let's find out this thing. How to find out? I don't know about this code. Let's find out this thing. So let me convert this first of all into the form of recurrence relation. Recurrence relation. What will be the recurrence relation of this? So let me write it as Tn. Fine. N is the size of the array. Binary search is used for finding the element inside an array. So array size is n. Okay, array size is n. So this is replaced with n. This thing. Fine. And this function we are calling here, and here the same function you can see, binary search function. Binary search function, but with different parameters. Actually, in binary search, what we do is, if this is our array, what we do, I don't know. Okay, let me write here 2, 6, I don't know, 7. I'm writing some element 9, 12, 13. So what we do in binary search, let me write one more 14. So how binary search works? If I'm searching for one element, let's suppose I'm searching for 7. Is the 7 available in my array? How binary search technique works? That will go to the middle, compare 9 with 7. Is the 9 equal to 7? No. Then I'm confirmed the 7 will be at the left hand side. Why I'm confirmed? Because binary search we can apply on the sorted array. Binary search we can apply on the sorted array. Although we can apply the binary search on unsorted arrays also. Okay, that is the more deeper part. But okay, in general we can say that binary search is applied on the sorted array. Okay, fine. So this is array sorted 2, 6, 7, 9, 12, 13, 14. Okay, so this is not equal. Then where we have to search? Confirm 7 will not be at the right hand side. 7 will not be at the right hand side because this is sorted array, and 9 is greater than 7. 9 is greater than 7. So we have to search at the left hand side. Again, we will use the same method in a binary search. We go to the middle. So this is the middle of this small array. Is 7 is greater than 6 now. So where we have to search? At the left hand side or right hand side? Right hand side. So this way we apply the binary search. Okay. So every time you are dividing the array into half, you are not comparing with the half elements every time. Every time you are not comparing with the half elements. So how many elements you are comparing? Half elements you are comparing. Either you will compare to the left hand side. This is the left hand side array. And either you will compare to the right hand side. So this is the right hand side array. So you are calling this function 2 times, and input size will be half and half, because either you will compare left side or you will compare to the right side. That's it. Okay. So and the other part, this part is taking constant time to execute. There's no loop in here over here. No function is here. No loop is here. This statement will execute one time. Okay. So constant. Now let me write the recurrence relation. Let me write the recurrence relation for this. This is also asked in many interviews. What is the recurrence relation of binary search? We can write Tn is equal to this recursive. See, here you can see that we are using if and else. If and else we are using. Either this function will called, either the second this function will be called. The both function will not be called together. Either I will search to the left hand side or either I will search to the right hand side. I will not search at both sides. I will search either left hand side or right hand side. So I cannot write both of them here. I will write one, because I will either go to the left or right. Both are same. So I write one time. Why one time? Because if and else is there. Either I will search the element to the left hand side or either at the right hand side. Okay. So I write it one time. Plus, how much time I'm taking? Constant. So this is the recurrence relation. That's it. This is the recurrence relation of the binary search. You can go to the Google. Google can help us. You can go to the Google and ask him what is the time complexity of this recurrence relation. He will tell you that will be log n. That will be log n. When you will solve this recurrence relation, There are various methods, master method and other substitution method, recursive tree method. You will find out this thing. Okay. Okay, fine. So right now you know how to create the recurrence relation. After that you can find it maybe by Google, or maybe, okay, let me give you the intuition. You do not need the recurrence relation solving methods. You do not need to know that also. You can find out directly also. How? See, if you remember in the previous lecture, I tell you, whenever you are dividing with 2, what should be the time complexity? Every time, here the value was n. Every time you were dividing n by 2, every call, every recursive call, either to the left hand side you are going or to the right hand side you are going, but you are dividing your input to n by 2. Every time you are dividing your input n by 2, and I already promise with you, whenever you see the divide, complexity is log n. Complexity is log n base 2, because dividing with 2. Okay, intuition also we can use for solving. Do not need recurrence relation solving methods. Okay. Okay, I hope you people get the idea here. Any question you can ask me. Don't hesitate to ask the question. Your questions are very important, because your question is not helping you only. They're helping other people also. They're also having the same question in their mind. So you're helping other people also. Please don't hesitate to ask the questions. So we have lots of example, otherwise don't need to worry. So the time complexity for this is log n, and recurrence relation is this. Let's try for this one. Can you tell me recurrence relation? Can you tell me the recurrence relation for this one? Okay, meanwhile, I'm taking one question. Karthik is asking, to execute algorithm in programs, which language will give the best result? I think Karthik is asking that. Let me come this side. I think Karthik is asking that which language take less time to execute the program. So if we compare C, C++, Java, Python, okay, C language take minimum time. C language is a middle level language. That is means you can directly communicate with the hardware in the C language. Okay, you, with the help of system calls, remains there in the operating system. So in the C language we can use the system calls directly, rather than writing, okay, printf statement or any cout statement. We can directly give print system call, okay, or read system call to read the data, write system call to write the data. So what I am telling you, C is the faster language as compared to C++. C++ is faster than Java. Java is faster than Python. Python is one of the lowest, having the lowest speed as compared to JavaScript and other languages also. Okay, Python is very easy language. Even a school student will start loving with the Python. Okay, they can easily understand the Python because Python is more human friendly. But Python actually, from compile time point of view, Python take more time, and that's the reason in some of the program, if you are a competitive programmer, then in some of the program you will find out the TLE error, time limit exceed, for the same code, same logic you are writing in C++, same logic you are writing in Python. For some of the problems you will find out, you will execute the code, you will find out TLE error, because Python take more time. Okay, and Python consume more energy also, heat up the processor as compared to C and C++ and Java. I hope you get your answer, Karthik. Karthik is saying all over non-language, only C or any other is there. So if you still want to go down than this, you can go to assembly language. Assembly language is also there. But if you will go with the assembly, means that is not user friendly. That is not human friendly. Okay, like you need to write add a comma b, multiply mul c comma d, So that is very means complicated. After that, machine language comes. That is the fastest. Nobody write in the machine. People write in the assembly also. These people these days we do not need to worry about assembly. You just pick any language. Do not need to worry. Our target is to get selected in one of the product-based companies. So you can pick any language based upon your interest. Okay. We already discussed in yesterday's session which language you have to use. Okay. Fine. So, okay, one question is there. When Adim is asking, sir, when we can expect the DSA advanced course after this fundamentals? So, DSA advanced course is expected. This is, I'm not sure, but still I'm giving a time that, okay, in the first week of March, I will start that. Because this course will take 1 month to complete to me. After completion of this course, I will build your fundamentals. Okay, then we will deep dive inside the advanced, and that case we will play with maths also, and programming language also. Okay, there libraries also. Okay, but I will give you all the fundas over here. In advanced one we will take lots and lots of mang companies problems, and different type of means different every problem will be covering some different logic. Like that I will be covering all type of questions. Again, practice will be requiring, but I will be covering each and every type of questions over there. Here I'm just want to make your interest in DSA. I want to make you feel that okay, DSA is not that tough. DSA is not that tough. It's not, if we put little efforts, then it's easy to go. Yeah, it is true, because the DSA is all logical, and we are human are good at logics. We are good at thinking rather than cramming the things. I hate this from at this point of view. Our education system, actually, our education system, in our schooling system, we are more focused on cramming the stuffs. I personally believe that okay, that should be replaced. As a teacher, that should be thrown out, because we are human. We are not good at cramming. I don't know, even the prime minister or president cannot also remember the things. Nobody. You can pick the anyone. Nobody can remember. We can logically think. So the DSA is logical. So we can fall in love with DSA. After DSA advanced course, Karthik, you will be confirm able to crack the product based company rounds, because you will be grilled in that. I will give you lots of questions. You need to do that questions. I will do all type of like all type of scenarios I will take in the class, and then I will give you the questions, okay, related to that. If you are doing that, confirm you will crack, because it's not nothing magic is going on, because we are covering each and everything, and they cannot ask out of syllabus. They cannot ask, then they need to ask from there only. And if you are covering everything, then that will be easy for us to go. Okay, fine, let's move on. So let's find out the time complexity of this code. Again, this is recursive code. You can see I'm calling this function again here and here 2 times. This time I'm calling. Okay, so okay, let me write the recurrence relation. So this is Tn. So now the value parameter is Tn minus 1. So let me write Tn minus 1, and this is also Tn minus 1. Both will execute. This will also execute. This will also execute. These are not in if and else. Both will execute, and this part will take constant time to execute. There is no loop or function over here. So recurrence relation writing is very easy. Tn equal to Tn minus 1, Tn minus 1 plus another Tn minus 1 plus this constant. So I can summarize it like Tn equal to 2Tn minus 1 plus 1. Can you people tell me? Can you find out in the Google right now? Okay, use the Google. Can you please tell me what is the, if you will solve this recurrence relation, what should be the time complexity? Can you please check out? Can you please reply? Anybody? Anybody? Can you please reply? Thomas already given the recurrence relation for this. Yes, Thomas, you are right. 2Tn minus 1 plus 1. Great. Can you please find out? Can you people please check out this one and tell me what is the recurrence? What is the time complexity? It's not T of n Vikalp. It's not T of n Vikalp. This is one of the worst algorithm. Yes, Rahman, you can survive with Python. You just pick any language. Uh, even you will not pick the Python also. You will go with pseudocode. You will be get selected in Google. I'm giving you the one promise. If you are saying that I can give you the logic, I can write, but in the pseudocode, they will love this thing because even you know Python, they will ask you, please learn JavaScript. They will not give you Python to work. Believe me, confirm. You can ask to anyone. They will not give you most of the cases because every project will be requiring different thing. They will ask, okay, please learn this language, and you need to work in this. Okay, so they don't need. Ultimately, they will put you in some project which will be which will belong to other language. So they will think that okay, it's okay. He will learn it. He will learn it. His logics are clear. His logics is clear, and you need to shift this thing. Whenever you will be in the industry, you need to learn the different languages. Okay, that will not take time. That will take 1 month. DSA learning logic building is lengthy one, 6 month minimum. This is what I'm talking with from my previous experience with the people. Okay, 6 month minimum, and that can go up to 2 years. Depend upon how much time you are giving, how much practice you are giving. If you're totally dedicated, 6 months. If you are moving slowly, if you're still walking, slowly, walking, it's okay. That may take 1 year, little bit more than that, maximum 2 year. If you have stopped, which is happening in 95% cases, people are stopping. They are not consistent. So that's why only 5% are going to the product base. Pankaj already give the answer. Bharat Bhushan also give the answer. I think that he is saying 2 power n. Karthik is also giving answer 2 power n. Yes, the complexity will be 2 power n. 2 power n. Okay. Okay, fine. I'm not going in further explanation because that will be requiring time. You can take this thing. Okay, the upper view you are getting, that is important. If the upper view will be clear now, then you will feel confident. Okay, understanding from this course, the motive is that you can see the map. You can see the map now. Now you can explore. You can go deep down and you can explore. Okay, so I'm not going very detailed. This can be solved by recursive tree method. Okay, because if we have multiple recursive terms, recursive tree method is the best way actually. Okay, fine. It's okay. Don't need to worry about that stuff. You know the upper stuff. You can move on. You can move on. Let me erase this stuff. Don't need to worry. Don't need to worry. Let's take this maximum from this session. Don't need to worry about the stuff. Okay. So this is your homework. You need to write the answer for this in the comment section. I will take in the comment only. I will not take here in the live chat. Please check out it at home. Share me the recurrence relation and share me the time complexity for this code. You can take the snapshot and you can try at home and you can reply in the comment section. Please try over there. Okay, fine. Let me move on. Okay, now let's move to the last topic for today. That is space complexity analysis. So that was left in the last lecture. We covered the time complexity now for the recursive also, and for the loop based also. Loop based we covered in the last class. Okay, in the second lecture. So now we will talk about the space complexity. Very easy actually. Okay. Okay, let's move to the space complexity. What is space complexity? Very easy. Space complexity of an algorithm means how much space that is taking inside the RAM. Okay, and there are two type of space that is taking. One is the input space and one is the auxiliary space. That's it. Total are making space complexity. And what is input space? This is the space required by the input given by the user. Let's suppose, for example, I am writing a code for sorting the elements. I want to sort n elements. I want to sort n elements. Okay, I am writing a code for sorting the n elements. Then my input space will be n. My input space will be n. Okay, maybe I'm taking extra space. Auxiliary space is nothing extra space you are using. You are taking some extra arrays, variables. You are taking some extra arrays, variables, extra space you are taking in your program. Maybe I don't know. Maybe if I'm taking extra space is n square. I don't know. So this is the extra space. Total complexity is n plus n square. N plus n square. And again, asymptotically you want to write, so remove the lower order term, so the space complexity will be n square. Okay, or maybe you can say that my input space is n. Another example, auxiliary space nothing. I'm not taking any extra space to sort the numbers, like in the case of bubble sort, selection sort, insertion sort, quick sort. So the complexity will be n plus 1. So you can write it order of n. This is the space taken by your algorithm. Okay, maybe you can write like n, or maybe your input space is 1. You're not sorting to let it sorting. Maybe another algorithm you have written, and another problem is there. Input space is constant, but auxiliary space is n. So total space complexity is 1 plus n. So that is again n. Fine, that's it. Very easy. What is the input? What is the space required to store the input, user input? And what is the extra variables, arrays you are using in your program to solve that problem? That is auxiliary space. Total are making space complexity. That's it. Very easy. If you understand this thing, give me the answer of this question. Can you tell me? What is the space complexity? What is the space complexity of this code? Can you tell me? Please try. Please try. Keep trying, keep replying. The God is watching. If I'm not watching, God is watching. Please keep trying, keep replying. What is the space complexity? We already know the time complexity of factorial is order of n, or you can say, okay, theta of n, time complexity. What about the space complexity? If anybody know, can reply. If anybody know, can reply. Right or wrong doesn't matter at all. That should not matter in class. Actually, the space complexity here is, for this one, we are finding the factorial of a number actually by using a loop. How we are finding? Very easy. Let's suppose we want to find the factorial of 5. We are executing a loop from 2 to 5 and multiplying every time, like 2 into, how this loop is, what this loop is doing, multiplying again and again, multiplying the next numbers and storing the result in res variable. Okay, so like multiplying 2 into 3 into 4 into 5, that's it, and store the result in this variable, and after that return this variable. That's it. Find the factorial of 5. That's it. This is how we are finding. That's it. How much space this is taking? Let's see. Okay, let's see how much space this is taking. Very easy. They provide, this is our input space. They give a, they provide a number to us, one integer to us. So let me write input space. Input space is a integer, just our integer, one integer. Okay, this is our input space. How much space is taken by one integer? Right now, actually, that depends upon compiler to compiler also. But these days, the compiler takes 4 bytes. 4 bytes to store one integer. Okay, so we consider, okay, 4 byte. 4 byte space is required for input, and plus. Do you use extra space also? Yes, I declare 2 more variables to solve this problem. I use 2 more variables. Both are integer. Okay, so auxiliary space. Auxiliary space. And how much is that? two two integer I use. One is res, one is I. To solve this problem, how much space this will take? 4 byte, one integer, 2 byte, two integer, 8 bytes. So what is the total space complexity? Let me write here. 4 byte plus 8 byte. How much? 12 bytes. 12 is a constant. 12 is a constant. I can write the space complexity is 1. 12 is a constant. 12 is a constant. The space complexity is 1. Even though I'm taking another variable, maybe other variable, maybe 100 variable I'm taking, maybe 100 variable I'm taking, I can multiply with 100. 1200, again constant, again in this category. Okay, so this is taking constant space to execute. The space required here is constant. That is constant. Any doubt you can ask me. Any doubt you can ask me. If no doubt, answer me this question. Another question. If no doubt, okay, this is the, let me erase it and make it more clear. So time complexity is n, space complexity is 1, auxiliary space is 1, extra space is how much? Two variables only, 8 bytes, 8 is constant. Simple, that's it. Okay, fine. Another one, another question. Please reply. Please reply. Can you tell me? Same factorial program, but this time recursive. This time recursive. I'm solving the same problem using recursion now. Using recursion. Here, I solve this problem using a loop. Using a loop. And here, I'm solving the same problem, finding the factorial using recursion. Okay. Same problem can be solved by recursion or by loop. We will talk more about it in recursion and in dynamic programming. Okay. But right now, anybody can tell me, let's see if anybody can tell me how much space complexity is here. Time complexity is same. We already discussed the recurrence relation was Tn equal to Tn minus 1 plus 1. And if we solve this recurrence relation, the time complexity was n. Time complexity is same here and here. Okay. But what about the space complexity? Any idea, just give the answer. It's okay. You just give the idea. We do not need to be right. We do not need to be right. Let me see if somebody can give the right answer. It's not order of 1. It's not order of 1. Anything else than order of 1? Anybody? It's not n factorial. It's not n. Oh, it is n. Yes, Vikalp. Let me choose the Vikalp answer. Yes, Vikalp, this is n actually. The space complexity here will be n. Okay, how this is happening? So time, what is the input space? Input space is only one integer. Okay, input space is 1 integer, 4 byte. That's it. Leave it. Let's see the auxiliary space, extra space. Actually, whenever we use the recursion, we use the recursion, Vikalp must be knowing this thing. Whenever we use the recursion, we store the previous function inside a stack. Whenever I will call the function for 5, factorial of 5, and then I will call the function for factorial of 4, then 3, then 2, then 1. So previous functions will be stored into a stack. Let me create the stack over here. F5 will go here, F4 will be go here, F3 will be go here, F2 will be go here, F1 will be go here. So before completing this, I need to complete this. 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 Okay, so these functions, previous function will be stored inside the stack by the CPU. We as a programmer not creating any stack over here. You can see we are not creating any stack over here. We are not using any stack. Who is creating this stack? CPU. It's the burden of CPU. This is not the programmer burden. Whenever we use the recursion, this makes the headache for the CPU, not for us. Okay, we can enjoy the recursion because in recursion make the code very concise actually. Okay, so whenever the next programmers come, he enjoy the recursion. He become able to understand the code easily. And maintenance is one of the important part actually. Okay, we will talk about the recursion in more detail, but right now I'm just telling you one thing. Whenever we use the recursion, one stack will be generated by the CPU to maintain the previous functions. So previous function will go into the stack because we need to maintain them, because we need to execute them also. So we need to store them somewhere. So CPU will store them into a stack. And what is the size of the stack? You can see 1, 2, 3, 4, 5, depending upon what is the n value. So this stack space will be taking n space. So auxiliary space, extra space for recursive program, this factorial recursive program will be n. Okay, we will talk about recursive program space complexity more in the case of recursion, because recursion will be whenever you will call, simply you can remember, whenever you will call the recursion, there will be a stack maintained by the CPU, and this is also extra space. And this space is, how many spaces there? 1, 2, 3, 4, 5, and that depends upon the value of n, that is n value is 5. So space complexity, auxiliary space, extra space is n. Okay, so the space complexity for this code is n. Total space complexity is n. Why? Because extra space will be taken for maintaining the stack by the CPU. Sarang, this is not the okay, Sarang is asking one question. He's saying that cannot previous function f5, f4, f3, f2, f, these will not go into the garbage collection? No, they will not go into the garbage collection. They, we still have the address of them. Okay, we still have address of them. We are maintaining the address of them. CPU is maintaining for us actually. Okay, they will not go in the garbage collection. Okay, they are not still wasted. They are not waste. Okay, in the garbage collection, those memories, those space will go whose record we don't have, okay. So the record we already have for these functions, okay, we need to maintain, because ultimately we need to solve the problem for n, not for n minus 1, n minus 2, n minus 3. Okay, so they will not go to the garbage. Fine. Okay, let's see. Any doubt here, you can ask me. Any other doubt, anything coming to your mind, don't hesitate. Otherwise, hooray, we have completed the third session also. Congratulations everyone, and only 15 sessions are left, and after these 15 sessions you will be found yourself good, you will be found yourself, okay, you know DSA. You can say to anyone, you know the DSA. You can argue with anyone, with the interviewer also. Okay, and that's it from my side for today. Thank you Mandeep, thank you Karthik for being with me for such a long time, almost 2.5 hours is there. Okay, and again I'm saying, okay, if you are finding these sessions helpful, if you really want to pay some fee to me, then please go to my previous sessions, give your feedbacks. Your feedbacks will increase the range of these sessions, and they will go to maximum students, and that will be that is my request to you people. So that's it for today. Tomorrow there will be no session Java. Next session will be on Monday. Okay, don't write this stuff in the comment. Okay, is there will be session tomorrow? The manager will schedule to for tomorrow itself. Okay, so Saturday, Sunday I will be on the leave. Monday we will start with fresh energy. Okay, anything you want to discuss with me, I'm here next for 2 minutes, 1 to 2 minutes. Anything, journal you can ask, any doubt from the topics you can ask. Otherwise, keep writing +1 if you really find this session helpful. Keep writing +1 in the chat box. Any doubt, anything you want to discuss, we can discuss that also. Otherwise, write +1 if you find this session helpful, please. Waiting for anything from your side. Okay, Karthik is asking one question. Do recursion create a different scope of variables? Yes, Karthik, uh, the, uh, the variable will create the different scope. Yes, every variable will belong to one particular function. Okay, we have declared it one time, when whenever we will call for f5, the variable value will be different. Whenever we will call for f4, the variable value will be different. Whenever we will call for f3, variable value will be different. Okay, every one will maintain its own. Right to learn is asking, do you conduct the offline classes? No, I don't conduct the offline classes. I'm just going for online classes only, and we will cover everything here. Don't worry, don't worry. We will make this free. Let's shut down the business of other people. Okay, uh, fine. Okay, so okay, then thank you everyone. We will meet on Monday. Till then, best of luck. Keep preparing. Keep solving the problems. You can practice. Join this course. Yes, I will complete all the chapters. 18 topics I have taken. Okay, and thank you everyone. We will meet on Monday. Bye bye. I'm ending the session.